Okay, so let me try to remind where we were. So we were really looking at this this hierarchical renormalization group, and I wanted to compute it to second order. That's what I wrote last time. Okay, and then we idea was that we start with, like always, with this guy, and then see what happens. So I want to compute, iterate it many times. So let's give it a name. And then iterating this, I want to write it in the following form. So there is a running mass term. There is a running coupling. And then there are all the irrelevant junk. And there's a recursion. And now n is getting smaller. Remember, this was no, sorry, not yet. No. So Rn plus 1 is L squared Rn. That was a relevant variable. And then there are some corrections, and actually I want to write them all because we need them all to understand the various problems. So let's put them. So there's gamma 1. There's a linear term. That's obvious. And then from the second order you get second order terms, and there are two of them. Something quadratic in the coupling, and then something quadratic like this. And then the rest I will write order lambda cubed. And you will understand in a moment why it will be lambda cubed. I mean, there should be also the R, etc. But let's come to that in a second. Lambda n plus 1 is L2 4 minus d, lambda n plus some b. L. Lambda n squared, and the rest is order lambda n cubed. And then the W, the junk, is some linear operator, the linear renormalization group acting on it, plus order lambda n cubed. And this contracts. This expands, but this contracts. And since it contracts, it turns out to be irrelevant in the analysis, and I will just drop it today. But of course, you will see a proof in the notes where it's taken into account. But let me not go to that. So let's go through the various cases we are interested in. Well, let's go to the easiest first. So bigger than 4 dimension. So lambda n decreases. Sorry. Obviously, this iteration it will go something like t minus 4 times n times the initial condition. So it's going to 0. If Rn is going to 0 too, okay? Well, Rn is not, doesn't seem to like to decrease. It's increasing. But of course, we wanted to find the critical point, R of lambda. So I want to fine-tune the initial condition for the R so that Rn goes to 0. Actually, I want to fine-tune it so that it will be of the order of lambda n. If that's the case, then the end result is that if I take my original v with that critical value, then this goes to 0 as n goes to infinity, which means that I'm converging to the Gaussian model, no interaction. Okay, so how would I find the oh, I still have this left. Okay, how would I find the R lambda? That's sort of a very simple idea of dynamical systems how to do it. You sort of just while you do this iteration, you sort of fine-tune it step by step. Okay, so you do an induction. So you find an interval. Let me call it Jn. It's an interval. So interval, so that if R belongs to this interval, so the original R, then Rn will be what we want. So how do we do that? Well, let me take the initial interval, for instance. Looking at that iteration, I could take, let me take, for instance, this. Okay. What happens to this so R is here? So what happens to R1? Okay. So R1 minus L squared R, according to this iteration, will be basically less than gamma lambda n and order lambda n squared. So if lambda n is small, this is less than gamma 1 lambda. Okay, lambda small. So it means that this R1, if I view it as a function of R, it maps this original interval, which I had in the beginning. It maps it to a much bigger interval, namely minus something like this, s squared minus 2 times gamma 1 lambda and L squared minus 2 gamma 1 lambda. So it maps it to a bigger interval. Okay.
You're describing R1 of J0.
R1 as a function of R. Okay. The new mass is a function of the original one. It tends to increase up to a small contribution from lambda. So obviously, and it will be a continuous function. So obviously, I can find a sub-interval from here, which maps. So here is the gamma 1 minus gamma 1 lambda, gamma 1 lambda, or 2. I can find a sub-interval which maps to this interval, which is minus 2 gamma 1 lambda 1. Remember, lambda 1 will be smaller than lambda. All right, but then I can do the induction. So if I look at Rn, I can find intervals. Jn is sub-interval of Jn minus 1. Strict, actually, such that if R so if my R belongs to this Jn, then Rn will be less than 2 gamma 1 lambda n. So my R critical of lambda is just the intersection of all these intervals. And since they are closed intervals included into each other, it will be just a point. So that's the critical point. So that's the end of the proof. So it's very easy to find the critical points once you are in this irrelevant situation where the coupling constant, where the interesting terms go to zero, tend to go to zero. Okay, what about d equal 4? Not much changes except that now lambda n plus 1 is b lambda n plus order lambda n cubed. So now everything of course depends what is the sign of b, but well, we have the formula there, so b it's explicit. Well, once you do these expectations, there are some stupid, yes?
Lambda n the first term, right?
Where?
Lambda n plus 1 is equal.
Squared.
The linear term is missing.
You need a linear term on the right hand side, there.
Ah, sorry. Yeah. Sorry. Thanks. So what is b? There are some irrelevant powers which, let me just write them anyway. But what's entering here is this correlation function. And this is positive because this is just the square by Wick rule, the square of the covariance. So b is negative. Well, if b is negative, then this tends to decrease. And to figure out how it decreases, just look at the corresponding differential equation. d lambda dn is minus, let me write it like minus b absolute value lambda squared. That's very easy to solve. I believe everybody can solve it, and the result is that lambda n is lambda over 1 plus n times b absolute value times lambda. It goes to 0 as n goes to infinity. And if you remember what I was doing my Fishy calculation yesterday, there was a Ginzburg-Landau version of this correlation function, but everything was done in one perturbation series of all scales, and I did some Fishy resummation and ended up with a very similar looking result. It's exactly the same result. But here it of course comes without doing anything like that. It's just the property of this flow close to the second order. Okay, so in 4 dimensions there is a critical theory for each lambda, but they are all Gaussian in the long distance limit, so they are all governed by the Gaussian fixed point, and that's indeed what we expect from our philosophical picture, because remember the stable manifold, unstable manifold consisted only of R in more than 4 dimensions, and now we found out that the lambda, which became marginal, was actually also on the stable direction. Okay, that's d less than 4. This fixed point is called the Wilson-Fisher fixed point. What happens when d is less than 4, lambda becomes relevant. So what I was doing there, however small lambda I start in the beginning, I will be killed going out of the perturbative region eventually. Except if and then of course I would need to do something else, and of course you can study this recursion by numerically, and that's actually what Wilson was doing in the with computers of those times. And indeed you find a new fixed point, but then there's a famous idea here by taking d 4 minus epsilon and considering epsilon small. In my hierarchical model, the d is still there, sort of written here as this sum, but I could actually modify this so that the d is really, I mean, this run from 1 to L to d, okay? So it's difficult to consider d is still non-integer here, but this behaves, it doesn't really matter what I have here, so I could as well consider the following iteration. And this is actually Wilson's original approximate recursion relation. So just simple convolution with Gaussian. Okay. Then d is an arbitrary parameter, and I can take it 4 minus epsilon. So what do I find? I find that lambda n plus 1 is L to power epsilon lambda n. And then let's put this b. Let me really. Okay, I have this b, but remember it's negative. There clearly is now a chance of having a fixed point, because this is 1 plus epsilon log L. And indeed, you can solve from that you have a fixed point lambda star, which is, what does it become? Minus log L over b times epsilon plus order epsilon squared. There's a non-trivial fixed point, and we have this picture. We have this picture that here's the Gaussian fixed point. It has unstable manifold, two-dimensional. There's an r and lambda direction, and then there is a non-trivial fixed point here at lambda star, which in this simple case is of the order of epsilon. So it's perturbative because I'm taking d close to 0. Okay, so when epsilon equals 1, and we are doing not hierarchical, but the real thing, we expect there to be a fixed point, which describes the critical behavior of this model, but also of the Ising model in 3 dimensions. And indeed, such a fixed point can be numerically studied.
Why you are not drawing this unstable manifold out of this fixed point?
Out.
Well, it's not intersecting the lambda at the fixed point. The unstable point.
Unstable.
Should go through fixed point, no?
Here's a new fixed point.
So there are 2 fixed points.
This is the one which is.
Figure 1. Okay.
This is the one which is infrared unstable, and this is infrared stable.
Somehow there must be some line going from above. You are not going to this fixed point.
Non-trivial fixed point, there's also a relevant perturbation with that.
Oh yeah, it has one. Okay, yeah. That you wanted. Okay.
Yeah.
It has it has still one unstable direction. Yes. Sorry. Which for small epsilon is just gotten out of the phi squared again. Okay.
It all depends on L.
No, it doesn't. Well, in hierarchical model, it's a parameter, but the L L is 2 or 3, okay.
Logarithm also.
Yeah, okay. In the real model, of course, it doesn't depend on L. In the notes, you can, I do the calculation, the complete calculation to the second order in the real model, and you get everything. But let's not go to that, okay. What about d equal 3? You can still study it, and now there. Well, what do you have? We have these two, r and lambda are relevant, like we noticed. But then there is also, what should I call it? U, phi 6, and U is marginal. It's very similar to 4 dimensions where we had one relevant and one marginal. So we could, of course, we could try to do the following. Given U, we could try to find a critical value of U, of R, and lambda. Both of the order of U. And ask about whether such a critical point exists. This is called a tri-critical point. And indeed, the same idea I did for the critical value of the mass, I can do here, exactly in the same way. I run out of batteries. Okay. It's better? We can do exactly the same thing, okay? And then the question is, what happens to this? And indeed, it turns out to be marginal. So the tri-critical point is perturbative. You can construct it exactly like I constructed the critical point in 4 dimension, and it's Gaussian. Gaussian as n goes to infinity. Okay, so Rn. But then, of course, you can take these 3 minus epsilon, and exactly like here, the tri-critical point becomes perturbative. So you get the U star order epsilon, and you get the non-Gaussian tri-critical point. Now you can keep on doing this business, going down with a dimension formally. Remember, if I take phi to power n, then how did this go? This goes like L to d minus n, d minus 2 over 2. So this becomes marginal at critical dimension dn equals what? 2n over n plus 1. And that way I can construct n critical points. And as n goes to infinity, the critical dimensions go to 0. So I have more and more fixed points in the renormalization group. In the limit, when I go to 2 dimension, I expect to have infinitely many fixed points. And indeed, when you study the non-hierarchical model, that's what you expect, and those fixed points actually have been found. In some sense, they are the minimal conformal field theories. Okay, so there is a rich structure in 2 dimension, which is very special. But apart from the 2 dimension, we have a finite dimensional unstable manifold, and there is sort of a finite number of things which can critically happen. Okay. That's the end result of this.
So each of these fixed points should correspond to the epsilon expansion below the n.
Which one? Here. Yeah. So here I had to fix n minus n minus 1. So to write critical, I have to fix two
You
variables.
always find the negative beta function
Yes.
for all of them.
Yes, in the true model. This calculation was, oh, it's done. Yeah, yeah, you can do it.
But can one see really that this in some formal or way that this the extrapolation
I didn't
of the
do it.
epsilon expansion corresponds to the minimal models?
Yeah, there is a nice argument, argument by Zamolodchikov by doing. I mean, there's a rich story in 2 dimensions. Okay, the renormalization group flow takes you from one fixed point to the other. There's a long story. Okay,
From one minimal model to the other.
but one to the other. Okay, it's a really nice picture. But
These are these quadratic models, so
what?
it is somehow connected with this quadratic model, so
QID. No, no. These are using model. I mean, these are. It's a long story. Okay. Let me not go to it because I still wanted to say something about much simpler things. Okay.
Antti?
Yes.
Your n plus 1 should probably be an n minus 2 or something.
I'm sorry.
The n, 2n over n plus 1, shouldn't that be 2n over n minus 2 or something like that? I mean, you want to get 4 for n equal to 4, no?
And also it goes to 2 as n2.
I want this to be 0. So did I solve it wrong? No. I did it. What did I do? Oh. Okay. So this equals 2. So that has to be 0. Yeah. So 2d over d minus 2. No, I want to solve for d. Okay. So d d times 1 minus d 1 minus n over 2. I shouldn't be doing this on the blackboard. So that's that's n. So d minus n. Okay, so d is n over
1 minus n half.
2n over n plus 1, n minus 1, n plus 1, yeah? N minus 1, oh, n plus 1.
n minus 2.
n minus 2.
N minus 2, okay, let's check when n is 3, 6, when n is,
N is 6. You get
6,
12
you
divided
get 6.
by 4, which is
4, right?
let me leave it for you. I believe in the notes I have the right calculation, but I'm not going to do it.
Antti, but
Yeah.
I think the comment about periodic models was interesting because just like normal CFTs presumably describe fixed points of local models, periodic CFTs might describe fixed points of hierarchical models.
Yes, I think it would be interesting to. I don't know. I don't think anybody studied two-dimensional hierarchical model whether it actually has this infinitely many fixed points. This is non-perturbative question, so it's not something which you can just do. I mean, you could numerically try to study it.
I think one can go from both ends. There is some literature on periodic CFTs.
Yeah, but it is going to be non-perturbative. Okay.
Yeah.
All right. Let's go back to the much simpler problem. So critical phenomena are easy, more than 4 dimension, subtle, less than 4 dimension, marginal in 4 dimension. Quantum field theory, the same thing, except that everything is inversed, so it's easy in less than 4 dimensions. Okay, and what did we try to do there? Remember, we had this sort of continuum picture where we had, so if we have cutoff L to minus n, then we were supposed to look at in the continuum picture some mass term, so times phi squared, something which might depend on the cutoff, and then something which we believe that didn't depend on the cutoff, namely the coupling constant. And then we wanted to find this guy so that continuum limit exists. very similar problem to the critical point, of course, but with some differences worth looking at. So what did that mean if we went to the dimensionless variables, which we like to do here? So that became L to power minus 2n an, and this became L to power d minus 4 n g phi 4. Okay, so this is what I want to take my hierarchical model, and let's put up here. So remember that it's our initial condition which we're trying to find. Okay, so this is lambda n, and this whole thing I call v of n. And then what was I instructed to do? I was instructed to renormalize it a lot. Capital N minus little n times. Apply that to v of n and take the limit as n goes to infinity. And I wanted to get something well defined after all this hustle, which was then the effect in dimensionless variables, the effective action of the quantum field theory. So the question is how to choose this thing here so that we have a limit. Well, it's the same iteration which is still hopefully there. Yes, okay, so we can okay, so that's iteration is there. So the only thing being that now when n is sort of decreasing in my iteration, because remember this was cut off L to minus n, so I should write this rather that I have, so I write this Vn. Let's not take the limit yet. So this, and let me not write that. Okay, so let me write that as Rn I squared plus lambda n phi 4 plus Wn, just like we did before, and everything is like before except that n is decreasing, so I have Rn minus 1 is L squared Rn, and then just like we had there, gamma 1 you see, we start with an astronomically small. If we are under 3 dimensions, we start really small coupling constant, and really small. This provided that the A is not too big. Okay, and so we have really small thing. We are iterating it, and it increases under iteration, and we want things to stabilize. Okay, well, let's distinguish dimensions. So what happens in 2 dimensions? Let me write this iteration so that it's actually better to write it back into the dimensional variable. So I call Rn. It wants to be something like this, right? Because it's increasing with L squared every step. So let's call it the way. Let's take it explicit and call the rest rho n, and then lambda n. Let me call it L to minus in 2 dimension d minus 4 minus d is 2, so this will be minus 2n. Let me call it gn. So this defines rho n and gn. So what is the iteration? So I get that gn minus 1 is gn plus order L to minus 2n gn squared. So this of course implies that gn will be g plus order L2 minus 2n g squared. So nothing really happens to that. But R is interesting. If I write rho n minus 1, so what happens to it? Well, it equals, in the leading order, nothing happens to it because I took this here. And then the next order, there is plus gamma 1 g from this term. And then the rest is small. Well, if I don't do anything, this guy, of course, goes down like this only if the row also goes down in the iteration. If I don't do anything, this is going to be disastrous because at every step I'm adding one piece, the same piece all the time, a constant. So I had to fine-tune the initial condition. I had to take the initial condition rho n to be such that this doesn't happen there. So I would take it minus gamma 1 times n times g. This means that my R n has to be minus gamma 1 n times L to power minus 2n g. This is very small still, okay? This blows up, but this doesn't blow up. So if I take that initial condition, then this n just keeps subtracting at each iteration, so I will get that rho n will be just minus gamma 1 n g plus order basically smaller order, like here. Okay, so that's the counter term. I have to take such an initial condition, and if I take such an initial condition, then everything, the iteration is under control, everything converges. So in the original variables, the quantum field variables, it says that I have to take the mass counter term to be that times L to 2n, so minus gamma 1 n times g. Remember, this was, the cutoff was epsilon, so this is a constant times log epsilon times g. So that's the source of the counter term. But you should see, it looks like something is diverging, but nothing is really diverging because in the dimensions variables, everything is all the time small. Everything is all the time perturbative, super small, until you start to go to the infrared. But as long as you stay in your iteration in the ultraviolet side, everything is small and you have a limit. Well, what happens in d equal 3? Well, d equal 3, there is a slight difference because okay, so I still have R n minus 1 is L squared Rn, the whole stuff which I probably erased, so I have to write it again. Gamma 1 lambda n plus gamma 2 Rn lambda n plus gamma 3 lambda n squared. But now lambda n minus 1 is what? L. T minus 4 is 1, so L times lambda n plus gamma 1 plus order lambda n squared. Okay, so what do I expect now? I still expect that lambda, so I start with very small thing, L to minus n lambda, so expect that lambda n will be still small, plus small correction. But in R, look what is happening. I mean, this is increasing with L squared here, every iteration step. This is increasing only with L, with factor of L. That was our problem there already. But this is also increasing with L squared. So this is sort of competing with that. It's doing the power counting with this looks like marginal. So I had to fine-tune Rn to second order. To cancel these guys which otherwise would increase. It's a simple calculation to find what it is, and I will not do it here, but you take the initial condition. Well, the first is you have to counter that, and that's easy. That's something like 1 minus L inverse gamma 1 times L2 minus n times lambda. All right, but what is the next term to counter those? There is another term which is, let's call it gamma 4 times n times L2 minus n lambda squared. I'm sorry, I was calling it g and not lambda, but oh, okay. So you have to fine-tune two terms. There are two counter terms. One which goes like, once you go to the dimension full variables, so the a n. There's one which is numerical factor times 1 over epsilon times g, and then there is another one which is a numerical factor times log epsilon times g squared. Once you choose that initial condition, then everything is again okay. Everything else will be higher order and contract. So that's the way super renormalizable. So you see, this is actually simpler than the infrared d bigger than 4. You can explicitly find these counter terms.
On the line above, is the L to the minus n? That's not 1 upon epsilon, it's very small.
L to minus n is epsilon.
Yeah, so what's the relation between Rn and An again?
No, I'm sorry. This was the field theoretical G. Yeah, I screwed it up. I mean, I started with I wanted to have a field theoretical. So in the dimensionful field theoretical variables, it looks like things are blowing up. Nothing is blowing up. I mean, it's just that you are once you go to the dimensionless variables, everything is small, as it should be, because this is a perturbative argument, and perturbative argument is not going to be valid if things blow up. Okay. Well, if you let d go to 4, then it's obvious. How did lambda n go? You get less and less from here, right? This goes towards 0. So if I look at the Rn minus 1, and then there is some function of Rn and lambda n, and also the irrelevant terms, but forget about them for this for demonstration. Now lambda n goes very slowly compared to that, so it's obvious that I had to fine-tune more and more terms. Okay, so I had to take the initial condition. Basically, I had to fine-tune more and more terms the closer I am to 4 dimension. So I had to take something like this. If you do the calculation, and if I didn't screw it up like I screwed up the tri-critical calculation, I had to find coefficients as a power series in the original coupling constant, in the coupling constant lambda n, all the way to the power, which is this, where the power of this keeps competing with the power of lambda squared. Okay, so I had to find through more and more counter terms to in the initial condition to have. All the time everything stays small, but only if I take the initial condition, fine tune it like that. Of course, it would be really silly to try to do it like this, because we could do it exactly the same way as we did the infrared critical point by shooting. So in practice, you wouldn't do it like that. I mean, you would just do the same argument I did for the critical point. This is exactly the similar problem. Okay. So t equal 4. What happens there? Well, lambda, let's write it again. It's like we had before. So lambda n plus b, lambda n squared, etc. And b was negative, so it's decreasing. So now now I can solve this, and let's solve it with the final condition. So let me try find lambda n as a function of lambda n as a lambda capital N as a function of lambda little n. So let's write it like this. This is lambda n divided by 1 plus b absolute value. B is negative, so that will be right. Stress that it's positive. Okay, this is my bare coupling constant, which I wanted to find. This is my running coupling constant at scale n, which I want to be sort of order unity or small. So you see that if I want to fix this, this is bound to go to 0. So as long as I keep so my did I write it correctly? Okay, no, I wrote it. I'm not going to get anything in this case around the Gaussian fixed point, because this is the lambda is in the end contracting towards origin. So unless I take my initial coupling constant so big that it's outside of this perturbative iteration, I have no way to construct a non-Gaussian continuum limit. That's the upshot. So, so in 4 dimension, as long as the lambda n are small, only limits are Gaussian. Okay. Things would have been very different if there had been a different sign here. So if this would have been like that. Then I would have my lambda would have increased when I do the iteration. So I would have taken the initial condition. Then I could have taken the initial condition. Did I write this correctly? I mean, I think I wrote something wrong. I think I wrote for this iteration, okay? So, you see, yeah, I wrote it exactly for the wrong. Okay, so let's go back. Okay, so that's what we have here. The solution of that iteration gives me, let's put it carefully. So I have b here and minus plus b. Okay. If b is negative, I can only, if I want this to be bounded, the only way I can do it is to have it 0. Okay. But if b is positive, I can take this to 0, like that, like proportional to 1 over n. So I can take the bare coupling constant to 0, and nevertheless have finite effective coupling constant. Okay, so I will take the bare coupling, which I call G. I will take it dependent on the cutoff, and take it like some fixed number divided by 1 plus n times whatever b times g. So if I choose it like that, then the effective coupling constant will be bigger than 0. That doesn't happen in our case, because in our case it had the wrong sign. It would happen if I, instead of considering 5-4 theory with positive lambda, I would take a negative lambda. Because if lambda were negative, then I would take the absolute value, call it the minus lambda again. That would shift this sign to the opposite, and I would have actually a continuum limit. And actually there is such a continuum limit if I take it negative. There is a non-trivial continuum limit for negative lambda. It's easy in hierarchical model. It's easy to construct, and it should be sort of not so difficult to construct for the true model also. Its only problem is that it will not be a reflection positive measure. But it has a perturbation expansion, which is the perturbation expansion, the renormalized perturbation expansion, which was constructed by people in the 50s, which I discussed in the first lecture. So there is a complicated story at 4 dimension. From the sort of physics point of view, in 4 dimension, there are very few theories which actually have this ultraviolet asymptotic freedom property, namely that the lambda, this fixed point is infrared unstable and ultraviolet stable. There are very few such theories, and actually the most well-known being the Young-Mills theory in 4 dimensions. And then there are some cases in lower dimensions where you have the same behavior, that you can construct a non-trivial continuum limit which is not of this super normalizable type. Okay? Yes?
I've heard you say there are infinitely many, you say the Young-Mills theory, but there are infinitely many Young-Mills theories, provided that you allow yourself to throw in an arbitrary gauge group.
Yeah, okay. Yes. Yeah, there are
almost all theories are.
Yes. Okay. There is a, I think, still a countable infinity. There is different gauge groups. You can add fermions if you don't put too many of them. Like in quantum chromodynamics, it's still asymptotically free. If you put too many, then it's not. But sort of the class of theories where this happens is very small. Okay, I think I was planning to give 10 minutes on stochastic differential equations, why exactly the same picture can be done for them, but I think time is over, so I won't do it. It's in the notes.
Questions? Max? Please? profit the questions to say 2 words on this partial differential equation. So.
I think people prefer to have coffee than I don't know. I mean, I can say, but I mean, I think it's
Convince the organizers to schedule an extra,
Yeah.
hour.
yeah.
Set 10 minutes.
Very quickly, so you have a differential equation with nonlinearity. You do exactly the same thing. You divide the field into block spin and the rest. But now you don't integrate on anything because you don't have no integral. You have an equation. So you solve for the rest. Plug it in and you get an effective equation for the block spin. So your renormalization group doesn't map actions to actions, but it maps equations to equations. So the nonlinearity, say for the phi 4 model, will be mapped to a new nonlinearity. The equation has a noise. You do it noise by noise. So then all the coefficients which we have here, the gammas, etc., are random variables. Their expected values are the ones which we actually have here, and they determine whether things are irrelevant or relevant, and their variances are sort of irrelevant. So in the end of the day, the counter terms are exactly the same for that reason. But this is very cryptic. So that's the answer to the question.
Yes. Going on with the PDE stuff, just a little bit.
Yes.
It sounds that the fact that you have a PDE could be helpful to treat it. When you write in this, you say, okay, I'm going to introduce this hierarchical model because there is this almost thing that is complicated and I want to raise it. And it seems that it is kind of true that since you have these PDE techniques, that part it's slightly easier.
That's a very good comment. One thing which I didn't have time, which I also planned, but I misplanned, I wanted to tell a little bit how we go beyond the perturbative approach here. There's a problem that these fields are unbounded, and this is called the large field problem in the business. And that's the cause of all the problems. Even in hierarchical model, you have to work a little bit, not just very little bit, but still a little bit. And in the PDE business, it sort of is done by PDE techniques. So you have an equation with nonlinearity, and you just show that certain bounds are satisfied. I mean, to me, it at least looks that it's potentially simpler in the PDE picture. At least the proofs, which I think Massimiliano will talk about that on Friday. So, so that's a sort of aspect which I think the constructive theorist should try to absorb from this PDE approach. And that's exactly the point. I think that's a good point.
If not, we thank you again.